In this chapter, we will cover bearing capacity of shallow foundations, focusing on pad and strip footings. Settlements are discussed separately. Foundation is a structural element like a column or a beam in a building. Its function is to transfer the load from the building to the underlying ground, safely and economically. The breadth, length, and depth of the foundation are denoted by B, L, and DF, respectively. When the depth is less than the breadth, it is a shallow foundation. When greater, it is a deep foundation. A pad footing carrying a column load, and a strip footing carrying a wall load, are two major types of shallow foundations. A raft carries multiple column and/or wall loads. In this chapter, we will focus mainly on the first two types, pad and strip footings. The deep foundations include single piles, pile groups, piers or caisson, and barrettes. When the load becomes larger, it is necessary to go for a pile group or a pier, which is a larger cast-in-place pile. In a pile group, a heavily reinforced pile cap connects the column and the piles. In super tall buildings, the column loads can be very large and we use barrettes for foundations. They look like trenches in plan view, filled with reinforced concrete, and take the shape of X, Y, I, cruciform, L, etc. The photograph on the left is of a square pad footing, with the column reinforcements in place. The one on the right shows a precast concrete pile being driven into the ground by a pile driving hammer. On left, you can see an octagonal precast concrete pile. The photograph on the right shows a 2x6 pile group for carrying a large load coming from an overhead bridge. The two major design considerations in both shallow and deep foundations are, A, bearing capacity, and, B, settlement. The first one requires that the soil surrounding the foundation should not fail, which is an ultimate limit state. The second one requires that the settlement should not exceed the tolerable limit, which is often small. This is a serviceability limit state. In addition, the foundation should be economical. There is no point in suggesting an overly large, over-designed foundation which satisfies both bearing capacity and settlement criteria. Presumed bearing capacity values are crude and conservative estimates suggested in codes, standards, and handbooks that would satisfy bearing capacity and settlement. They are useful in sizing the footing for preliminary estimates without any calculations or soil data. More rigorous computations are later required to determine the bearing capacity precisely. When a foundation fails in bearing capacity, the failure mode is different, depending on how compact the soil is. This applies to both granular soils and cohesive soils. The three failure modes are punching shear, local shear, and general shear. We will focus mainly on general shear failure in soils that are very compact, dense sand or stiff clay. You will not want to build a foundation on loose ground. You will compact and make it dense before placing the foundation. General shear failure occurs when the foundation pressure is the maximum, which is the ultimate bearing capacity. When general shear failure occurs, the soil surrounding the foundation is pushed down and laterally, sliding upwards along the failure surface shown in the figure. This results in visible ground heave near the foundation, which will not be noticeable in punching shear failure mode. The plot of applied pressure versus settlement would clearly define the ultimate bearing capacity, where the bearing capacity failure occurs in general shear failure mode. With so much uncertainties in determining the soil parameter and loadings, and the simplifications in the design methods, we want to stay well below this maximum value. We divide this by a relatively large factor of safety of 3 and use that pressure in the designs as our allowable bearing capacity. The consequence of a foundation failure can be severe. Terzaghi proposed the first rational equation for the ultimate bearing capacity of a strip footing. The equation contains contributions to the ultimate bearing capacity from 3 separate components: cohesion, surcharge, and self-weight of the soil. He introduced 3 bearing capacity factors NC, NQ, and N-gamma, which are functions of the friction angle. The ultimate bearing capacity equation was slightly modified for square and circular footings as shown at the bottom of the slide. Being the first ever attempt at developing a rational bearing capacity equation, there are few problems with Terzaghi's assumptions. He assumed the angle alpha is equal to the friction angle phi, whereas it appears to be close to 45 plus half phi. Also, he assumed the soil above the foundation level as a surcharge and neglected the shear resistance within this region. The expressions from Reischner, 1924, and Prant, 1921, are mathematically rigorous and widely used for NQ and NC. The problem is with N-gamma. There are more than 60 different expressions reported in the literature for N-gamma. The ones proposed by Meyerhof, 1963, Brinch-Hansen, 1970, and Vesic, 1973, are the most used in the profession. The plot compares the values of N-gamma determined by some of these popular expressions. At the footing level, there was already the soil overburden pressure gamma dF. This has to be subtracted from the gross pressures to arrive at the net increase in the pressures. The factor of safety must be defined in terms of net pressures. Most of the time, the gross values are much larger than this gamma dF, and hence, this exercise makes little difference. It matters when gamma dF is quite large. Here, we have the general bearing capacity equation, common for square, rectangular, and strip footings. We used Herzog's original bearing capacity equation as the basis, and include some correction factors to account for the shape, footing depth, etc. Meyerhof's method allows 3 such factors, whereas Brench-Hansen allows 5 and Vesic allows 6. In this presentation, we will use Meyerhof's method, which is quite popular worldwide, and is simpler than the other 2. It does not allow for the base inclination and ground inclination, which are not common anyway. Here is the Meyerhof's bearing capacity equation with the shape, depth, and inclination factors. When using Meyerhof's equation, use Meyerhof's and gamma. When using Vesic's equation, use Vesic's and gamma. Never mix them. A point within the ground on the vertical centerline of a circular footing is under axisymmetric loading. A square footing may also be approximated as a circular footing and hence applies axisymmetric loading to the underlying soil. A strip footing applies plane strain loading to the underlying soil. Here, all deformations and strains are along a transverse plane, with no strains in the longitudinal direction. The friction angle phi is about 10% larger for plane strain loading compared to axisymmetric loading. Therefore, when using friction angle from a triaxial test, for a strip footing, we should increase it by 10%. The loading beneath a rectangular footing is between that of axisymmetric and plane strain loading. The equation given here interpolates the friction angle on the basis of the footing shape given by B on L. In the short term or when the loading is very quick in clays, there is no time for drainage and the loading can be assumed to occur under undrained conditions. In such circumstances, we carry out a total stress analysis using Cu and phi u equals 0. When phi u equals 0, Nq equals 1, and N gamma equals 0. It can be shown that Nc equals 5.14, which is 2 plus pi. First step is to always carry out the plane strain correction to the friction angle. Use this corrected angle in determining the bearing capacity factors. Then, determine the shape, depth, and inclination factors. When there are horizontal loads or moments, there will be eccentricities in the resultant column load. That is, the column load Q is not at the center of the footing anymore. The eccentricity reduces the bearing capacity. Meyerhof, 1963, suggested disregarding the dark yellow area shown in the figure, which makes the load acting at the center of the remaining area, which is the effective area of the foundation. In this quiz, we give you the loadings on two strip footings as given by the structural engineer. What would you use for the eccentricity and inclination in the bearing capacity equation? Try to locate the resultant force at the base of the footing, which would clearly give the answer. In the figure on the left, the line load Q acts on the strip footing with eccentricity E. Let's measure the distance x from the center line as shown. The eccentric load can be seen as eccentric load Q plus a moment m equals Q times E. By the principle of superposition, we can add the two and determine the pressure distribution beneath an eccentrically loaded strip footing. The pressure distribution beneath the strip footing is linear, with maximum and minimum values as shown, at the two edges. To ensure the soil beneath the entire footing is in compression, the minimum pressure has to be positive, implying the eccentricity must be less than B on 6. Here for an eccentrically loaded rectangular footing, we have to determine the vertical pressures beneath the footing in terms of the Cartesian coordinates. We convert the eccentric load into eccentric load in two moments my and mx. The equation at the bottom defines the vertical soil pressure at any point beneath the footing. From the general expression, we deduce the expressions for the maximum and minimum soil pressure, which occur at two corners. The light green rhombus shown on the right is called kern. If the load acts within the kern, the entire soil beneath the footing is in compression.